I went back to Ohio, but my city was gone. There was no train station, there was no downtown. So town had disappeared. All my favorite places, my city had been gone.
Morning, everyone.
Reduced to parking spaces. Hey, oh, where to go, Ohio? Oh, I went back to Ohio, but my family was gone. I stood on the back porch, there was nobody home. I was standing amazed. My childhood memories so swept past like the wind through the trees. Hey, oh, where to go, Ohio?
Sorry, I have to interrupt this for a moment. Trying to sign into Zoom and it's not working. All right.
I went back to Ohio, pride. The farms of Ohio have been replaced by shopping malls and music in the air. From Seneca to Cahoga Falls, said, hey, oh, where to go, Ohio?
All right, morning, folks. You can ask homework questions. I mean, you could ask them here before class starts. That'd be a good place to do it. You could also ask them in the tutorial. We'll be posting office hours as well, so you can ask them there too. I mean, so essentially everywhere. First web work has not been opened up yet. So we've been looking at limits. By the way, this was Chrissy Heim, Chrissy Heim and the Pretenders. It was Chrissy's birthday last week, so I thought we would pay tribute. All right, so we were looking at limits and using limit laws to evaluate limits. Let's look at one more property of limits known as the squeeze theorem. What does the squeeze theorem say? Suppose you have three functions. You have three functions, f, g, and h, which are governed by the following inequality. For values of x near a, but not necessarily at a. Right, so you have this inequality. Yeah, I have not posted office hours yet because I don't have time to see anyone. Hopefully I'll post some later on in the week. So suppose you have this scenario. Furthermore, suppose the limit as x goes to a of f of x exists and is L, and the limit as x goes to a of h of x exists and is L as well. Right? So in other words, this function goes to L, this function goes to L. Then the middle function must go to L as well. Let's illustrate with an example. So I'm offering this without proof, squeeze theorem. And let's consider the limit as x goes to 0 of x squared sine 1 over x. Where does the difficulty arise here? Observe, first of all, you know how sine behaves, right? You know the graph of sine x, maybe not the graph of sine 1 over x, but certainly the graph of sine x. And what is happening? So what about sine of 1 over x? Well, what is happening to x, or rather, what is happening to 1 over x as x goes to 0? Well, you know what's going on there, right? I mean, it's a limit. Limit of 1 over x as x goes to 0. You've got a 1 over 0. So in the context of limits, this is some sort of infinity. Thank you. Right? It's some sort of infinity. In fact, if you are approaching 0 from the right, this is going to be positive infinity. And if you're approaching 0 from the left, it's negative infinity. So here, depending on whether you're going to 0 from the left or from the right, I mean, if we concentrate on 0 from the right, this thing is going to go to infinity. So that really the question is, what is the behavior of sine as you go to infinity? Well, I mean, we have the sine graph right here. And you see what's happening? As x gets larger and larger, sine isn't going towards one specific number, rather it just keeps going, taking on values between -1 and 1. And same on the other side. Consequently, sine of 1 over x, the limit as x goes to 0, does not exist. You're not approaching one unique value. So this part of the limit does not exist. But, of course, you know the behavior of x squared, and this part goes to 0. So there's hope. There's hope that the limit might actually exist. And the claim is that the limit is actually 0 via the proposition given to us by Eddie here. Right? I mean, this part goes to 0, this part does not exist. I claim that the limit is still 0, and let's prove that. By getting rid of this issue, the sine of 1 over x as x goes to 0 does not exist. The limit does not exist. But you know some things about sine. You know that sine is always between -1 and 1. So sine is between -1 and 1. Sine of theta for any value of theta. So in particular, sine of 1 over x is always between -1 and 1. Rachel is asking, why doesn't it not exist? Well, I mean, just take the case where x goes to 0 from the right. 1 over x goes to infinity. So really, we're asking the question, what is the behavior of sine as you are approaching infinity? And, well, I mean, sine just keeps going. For larger and larger values, you're not approaching one unique number. Well, I mean, it's just an argument. Somebody's asking, how can we know the limit of sine 1 over x as x approaches 0 does not exist without graphing? You know the behavior of sine x. We never actually graphed sine 1 over x, right? We just graphed sine x and made use of things we know. So you know the graph of sine. And as x gets larger and larger, sine just keeps going between -1 and 1. It's not approaching a unique number. So that's why the limit of sine 1 over x as x goes to 0 does not exist. One over x approaches infinity. Right, because it's a 1 over 0. We understood that last week. Why do we think that the limit of the function is 0? Well, I mean, let's prove it. It's not that we think. I mean, I'm making this claim, but now we need to prove it. Do I mean 1 over x does not exist, but when it goes to sine 1 over x, it exists? I do not mean that at all. I'm saying that 1 over x goes to infinity as x goes to 0 from the right. And consequently, sine of 1 over x as x goes to 0 from the right does not exist. The limit does not exist. The limit as x goes to 0 from the right, sine 1 over x does not exist. Right, because it's the behavior. Can we describe the behavior of this function as x gets closer and closer to 0? Well, as x gets closer and closer to 0, this is getting closer and closer to infinity. So what is the behavior of sine for large values? You cannot describe that. It's not going towards one value. It's not going towards one number. It just keeps going. That's why the limit does not exist. So since you know that sine is sandwiched between -1 and 1, sine of 1 over x is going to be between -1 and 1. And now let's multiply the whole inequality by x squared. X squared is a positive quantity, so the inequality is maintained. And we get negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared. And now we're going to use the squeeze theorem. Notice that the stuff in the middle is exactly what we're looking for. Let's take, well, I mean, it's easy to see that as x goes to 0, x squared goes to, it's just a polynomial, so you can plug in. Why did we do the inequality? Well, I mean, we don't know what this limit's going to be, right? I mean, it's 0 times does not exist. So how do we take care of that? We're going to take care of that by getting rid of the stuff that does not exist. Sandwiching it between two things that are easy to evaluate the limit. And as everybody has pointed out, this limit is 0. Similarly, on the other side, you've got negative x squared. So the limit is going to be negative 0, which is just 0. And consequently, by the squeeze theorem, the stuff in the middle goes to 0. How are we doing? Is the squeeze theorem only used for sine or cos? Not necessarily. And let's illustrate with another example. How do we know sine of 1 over x is between negative 1 and 1? Well, we know sine of theta is between negative 1 and 1 for all theta. So it's true for 1 over x. Zuhair is suggesting, so 0 times a limit that does not exist is 0. We don't want to conclude that. That is not the case. It's true in this particular instance. So the goal is to get the function we want in the form of an inequality where the upper and lower functions have the same limit. Exactly that. Exactly that. Can you prove the squeeze theorem? We can prove it. We're not going to prove it, at least not immediately. And let's do a few more examples, and then I'll show you how you can prove it. Consider this scenario where you don't even know what the function is. You have some function, g of x, which satisfies this inequality. Interestingly enough, you can still evaluate the limit of g, even though you don't know what g is. But if he's asking about functions with absolute values, we're going to do that immediately after this. Sorry, this is from page 102. Yeah, exactly, same page we were doing last time. Well, I mean, we know nothing about the function, right? We don't even know what the function is. All we know is it's sandwiched between these two things. So obviously, we're thinking squeeze theorem. And as x goes to 1, what is the limit of the left? Right, as x goes to 1, 2x goes to 2. It's just a polynomial you can plug in, right? I mean, it's one of the properties of limits. Limit of the right, again, a polynomial. So you can plug in. And as x goes to 1, you get 1 minus 1, which is 0, plus 2 is 2 again. So by the squeeze theorem, the limit must be 2. Con is asking for question 42. Oh, I actually have it down here. I was going to do it, and then I wasn't. So since you're asking, let's do it. Cameron is asking if there are cases where two sides of the inequality are not the same. Certainly, but then the squeeze theorem will not help you. For the squeeze theorem, you need the two limits to be the same. Jasmine is saying we start from range of sine 1 over x because x approaches 0, the limit of sine 1 over x does not exist. Exactly that. You want to get rid of this business that does not exist. What would happen if the limit of the inequalities aren't the same? Then there's no conclusion. No conclusion. Squeeze theorem does not apply. When you know to use the squeeze theorem, just by looking at the question, very useful in a situation 0 times does not exist. We're very far from L'Hopital's rule, Naomi. We will get to it, but near the end of the course. Is E inside the square root? It is not. Like this. So again, let's look at this. Let's look at this, and you see the issue here, right? I mean, this is going to go to 0 by properties of limits, right? It's just a root function. And now this sine pi over x, well, in the same sense that sine 1 over x did not have a limit, sine of pi over x is still not going to have a limit, right? This is going to go to infinity. And the behavior of sine as you approach infinity is not a unique value. So that's not going to exist here. And consequently, the exponential is not going to exist as well. But the same trick can be done here. You know that So it's again going to be 0 times does not exist, suggesting perhaps to use the squeeze theorem. And you know, I mean, the first two steps are the same. Sine of theta is between -1 and 1. So sine of pi over x is also going to be between -1 and 1. And consequently, the exponential function, which you know to be an increasing function, right? So e to the whatever is going to be less than e to the 1 and bigger than e to the -1, right? If you take 3 values governed by this inequality, A, B, C, right? Then e to the A is going to be less than e to the B, which is in turn less than e to the C. So you have this. Multiply the whole thing by square root of x, which is positive. We don't have e to the infinity here. Convince yourself, right? Sine is always between -1 and 1. Sine never does not approach infinity. So multiply by root x, and we get e to the negative 1 root x less than or equal to root x, e to the which is less than e to the 1 root x. Now, observe that the left and right-hand sides of this inequality are easy to evaluate. They're just constants times root x. And as x goes to 0 from the right, root x goes to 0. So you have e times 0, which is 0. Same on the other side. And consequently, by the squeeze theorem, this is 0. Would square root of x be negative or undefined if the limit was going to 0 from the left? It would not make sense, right? Going to 0 from the left, meaning you are taking negative numbers. You cannot take the square root of a negative number. So this question wouldn't even make sense. When we multiply a limit that equals 0 by a limit that does not exist, will we always get 0? No. You don't want to read too much into this. These are very specific to these examples. Why didn't the inequalities reverse? Because it's an increasing function. Exactly that. Why is the inequality set between e to the 1 and e to the minus 1? Well, because of this property, right? The exponential function is an increasing function. Call this a, b, and c. So if you take three numbers, a, b, c, where a is less than b, which is in turn less than c, then their image will follow the same inequality. Again, this is very specific to increasing functions. There was discussion about absolute value. And let me introduce a nice property of the absolute value. What is absolute value of 2? You know what it is. It's just 2. What about absolute value of negative 3? You know what it is. And that is just 3. We're going to rewrite this as negative 3. You know negative times negative gives you positive. Why would we want to do that? Well, in order to define the absolute value of x as a piecewise defined function. If x is positive, the absolute value of a positive number is just itself. So the absolute value of x, as x goes to, the absolute value of x, if x is positive, is just x. If x is negative, though, the absolute value is negative of itself. So if x is negative, the absolute value of x is negative x. And this will help us to evaluate. certain limits. Let's take an example. Suppose you wanted to evaluate limit as x goes to 0 from the right of absolute value of x over x. This rule only pertains to absolute value. Right? Well, observe here, we're looking for the behavior of the function as you approach 0, but from values bigger than 0. So x is always positive. So absolute value of x, when x is positive, that is x. And this limit is just 1. The greater than or equal to can be put on either one, it doesn't matter. You don't want to put it on both, because you don't want that ambiguity, even though there really isn't, but there it is. Let's investigate the limit from the other side. Mohammed is asking if we approach a squeeze theorem differently, if the limit tells us to approach a number from a specific side. The answer is no. I think you can approach it in the same way if the squeeze theorem is what you want to use. Consider this. In this case, we are looking at the behavior of the function as x approaches 0, but from values less than 0. So absolute value of x for values less than 0 is going to be negative x. And that limit is easily seen to be, thank you everyone, negative 1. What can we conclude about the limit as x goes to 0? You tell me, does not exist, absolutely. Let's try one from the book. So I've rubbed it off now, but somebody wants to reconsider this piecewise defined function. Let's do it. Right, so my question to you is, what is the absolute value of 4? And you know what that is. Absolute value of 4 is just 4, right? When your function is, when the values are positive, the absolute value is just x itself. But when the numbers are negative, what is the absolute value of negative 5? Well, you know that it's 5. And 5 can be viewed as negative 5. So you see the absolute value of a negative number. This is the number here. This is your x. This is the number. It's negative of your number. There it is. So that's why. Observe. Here, x is negative 5. So x is -5, so you plug in -5 in here and you get -5, which is the answer you were expecting, namely 5. But now we're kicking it up a notch and we have absolute value of x plus 4. So what is that? Well, I mean, it's just a composition, right, of absolute value of x with x plus 4. So in other words, everywhere you see an x plus, everywhere you see an x in your function, you replace with x plus 4. So absolute value of x plus 4 is going to be x plus 4 if x plus 4 is bigger than 0. And then it's going to be negative x plus 4 if x plus 4 is less than 0. Alexis is asking, why is the limit of x over x equal to 1 as x goes to 0? It is not. It is not. We're saying the limit does not exist. Limit from the right is 1, but limit from the left is -1. These do not agree, so the limit itself does not exist. Let's continue cleaning that up. It's x plus 4 if x plus 4 is bigger than 0, or equivalently, if you bring the 4 to the other side, if x is bigger than or equal to -4, and it's negative x plus 4 if x is less than -4. All right. We're looking at the limit as x goes to -4. So let's evaluate limit as x goes to -4 from the left and from the right. By splitting it up and looking at each piece separately, this will allow us to get rid of the absolute values. So for values less than -4, if x is less than -4, absolute value is negative x plus 4. As was suggested, perhaps we want to factor out the denominator, maybe factor a 2 out of there, allowing us to cancel the x plus 4s. Leaving us with a limit of, I think it was mentioned earlier, -1/2 earnings. Similarly, the limit from the right, when x is bigger than -4, right? When x is bigger than -4, absolute value of x plus 4 is just x plus 4. And if we factor out a 2 from the denominator again, you see that these cancel out, leaving you with a limit of, everybody sees it, I'm sure, 1/2. Absolutely. Would substitution not work here because you get a 0 over 0? Exactly that. Substitution doesn't work because 0 is, because -4 is not in the domain of this function. You get a 0 over 0, and who knows what happens there. We've seen many instances already, right, where 0 over 0 gives us different values. Here, 0 over 0 gives us positive 1/2 in one case, negative 1/2 in another case, and so on and so on. All right. It should have said 2 times x plus 8 here, thank you. All right. Sophia suggests you can tell it doesn't exist just by looking. I don't know that to be true. But I mean, if you can tell, that's very nice, but you got to prove it. And this is what I'd be looking for on an exam. What if factors in cancel for a similar example? Well, exactly, right? So you got to be prepared to adjust. Does the limit ever exist if there's an absolute value? It does, absolutely. Yeah. If I'll let you evaluate the following, but if you had something like this, then the limit would exist. This is not squeeze theorem necessarily. I mean, well, not squeeze theorem in this particular case, but you might be asked, or well, not asked, but I mean, the question may call for a squeeze theorem if you have absolute values. That could happen. When evaluating limits for absolute values, should we always break it up into limit from the left and limit from the right? In many cases, yes. In many cases, you want to do that. It's not always absolutely necessary. So again, you have to adjust. Martin, we did a squeeze theorem that did not involve trig functions. I'll have you, number 40. Number 40 we did. Okay. Was it 40? It was. All right, but can we solve the problem you just wrote down? No, I'm going to let you solve it. It's very easy. If you followed what we did here, you'll have no problem doing this. Split it up into left and right-handed limits. See what happens. So to know if the limit exists with absolute values, you have to take limit from the left. And, well, again, you have to adjust. There's never an always. In math, you have to be able to adjust. Now, I mean, we've been looking at limits and techniques to evaluate limits, and I'm sure a lot of you still have a lot of confusion. What's really going on here? The limit is a behavior. What does that mean? If you look at the definition we gave, we said that limit as x goes to a of f of x is L, if f of x can be made arbitrarily close to L by taking x sufficiently close but not equal to a. I mean, that seems very vague. And that's the problem with limits. Vagueness and hard to work with because of this terrible definition. And you're thinking to yourself, that's not what math is. Behavior of the function sounds more like psychology. What's really going on here? Well, what's really going on is that you're right, it's not the real definition. It's not a rigorous mathematical definition. And the reason that we haven't given you the real definition is because you won't like it. Let me give it to you now. Definition, we say the limit as x goes to a of f of x is L if epsilon greater than 0 is given, there exists a delta greater than 0 such that if x minus a is less than delta, then f of x minus L is less than epsilon. This is the real definition. Very nice. People who did this question got 0 for both left and right-handed limits, and consequently the limit itself is 0. Very nice. So this is the real definition of a limit. And let's look at what's happening geometrically. And you'll see that it coincides precisely with the vague definition that we had given. We're saying that the behavior of the function is L. In other words, f of x can be made arbitrarily close to L. How close? Arbitrarily close, epsilon close, right? The difference between f and L is at most epsilon. So L plus epsilon, L minus epsilon. Right? So we're saying that by choosing x very close to A, how close? Delta close, right? So this is A minus delta and A plus delta. By choosing the x's in here, you're guaranteed that your function is mapped somewhere in there. So by choosing x sufficiently close to A, but not equal to A, f of x can be made arbitrarily close to L. That's the definition of a limit. Let's take some examples. Limit as x goes to 1 of 2x plus 3. Well, you know what that limit is. What is the meaning of those symbols? They're just, right? Think back to the definition, the original definition we wrote down for limit. F of x can be made arbitrarily close to L. What does that mean, arbitrarily close? Well, this is the arbitrary, right? F of x can be made arbitrarily close to L. How far is it away from L? It's epsilon. Very small number, epsilon. By taking x sufficiently close to A. Let's illustrate with this example. You know this limit is 5, right? This is a polynomial. You know you can just plug in by the properties, by these limit properties, these limit laws we saw last time. Now let's prove it. Let's prove it by taking some epsilon. Let epsilon greater than 0 be given. we have to find a delta, right? So if epsilon greater than 0 is given, we have to show there exists a delta for which this works. Sometimes referred to as the Epsilon-Delta game, right? I give you an epsilon, you give me a delta, which works. Hours of fun. Let epsilon greater than 0 be given. I claim right, so x minus a, in this case a is 1. If x minus a is less than epsilon over 2, I claim delta, in this case, is epsilon over 2. If this is the case, then observe what happens to the difference between your function minus the proposed limit. We have to show that this is less than epsilon. But what is this? This is 2x minus 2, right? 3 minus 5. Let's factor out a 2. Let's not worry about the exam right now. Let's concentrate on learning this material. It's great stuff, and it makes you appreciate the way we were doing limits before. Hartley is asking, where did the over 2 come from? Where did the epsilon over 2 come from? It's an excellent question. Let's postpone that discussion until the end, and you'll see that it works out nicely. So we have, what do we have? We have 2 times x minus 1 in absolute value. Now the absolute value of a product is the product of the absolute values. And you know what the absolute value of 2 is. It's just 2. And now you see you have this absolute value of x minus 1. And that is less than epsilon over 2. And 2 times epsilon over 2 is epsilon. Success. We needed to show that this was less than epsilon, and that's exactly what we did. How can you find the delta without you giving it to us? It's an excellent question. So, I mean, with a lot of practice, you start to see what the epsilon has to be, but in the beginning, you don't know. So call it, I said epsilon, but I meant delta, right? At some point, you start to see what the delta has to be, but in the beginning, you don't know. So call it delta. You're up to here. This is going to be less than delta. So it's less than 2 delta. And what you want is really epsilon. So consequently, delta has to be epsilon over 2. Right? So you have no control over epsilon. Epsilon, I'm giving to you. You have to show there exists a delta. You have to find the delta. Let's try another one. Let's look at x squared. Yeah. Let's look at x squared. Again, you know exactly what the limit is. What is the limit supposed to be? It's supposed to be 0. So 0. So So let's prove that it actually is 0 using the Epsilon-Delta definition. Right? What do we have to do? Let's write down what needs to be proven. If epsilon greater than 0 is given, we must show, because I've rubbed off the definition now. So we must show there exists a delta such that if x minus a is less than delta, then f of x minus the proposed limit is less than epsilon. You see it, right? So we start with this. And what is that? Well, that's just absolute value of x squared, which is just absolute value of x times absolute value of x. And now you see that absolute value of x is less than delta. So this is less than delta times delta, which is delta squared. You wanted everything to be less than epsilon. What are you going to choose for delta? Who has it? If you want to make this less than epsilon, or equal to epsilon, right, because you already have the inequality, delta should be root epsilon. And you're done. It has to be the positive square root, right, because we want delta bigger than 0. There you have it. Very nice. Well, I've rubbed it off now, but this is x minus a, and this is f of x minus l. Look back at the epsilon delta definition. Khalil is asking the same question as last week. We still have to postpone that until Wednesday. Can it be smaller than root epsilon? And yes, that's fine too. So really, root epsilon is like the largest number you can take, the largest. How do we know root x is less than delta? We have it right here. That's the assumption that is made. One of the limit laws was that the limit of a sum is the sum of the limits if both limits exist. Right? Limit of a sum is the sum of the limits, assuming both limits exist. Let's prove this using the epsilon-delta definition. So all of these limit laws can be proven using the epsilon-delta definition. Perhaps we should postpone this until Wednesday, since we are out of time. I'll let you try to prove this. We'll prove it in class on Wednesday. So practice this epsilon-delta definition, the squeeze theorem, and we'll pick this up again on Wednesday. There is practice for this in the book. I don't have the actual page, but I'm sure it's the section that follows. We were doing page 102, so I'm sure it's the section right after that. Thank you, everyone, for coming. I will see you on Wednesday. I recommend doing all the exercises. So practice the squeeze theorem, practice this epsilon delta, and we'll pick this up again on Wednesday. You guys have a good one. I'll see you then.